Good evening, everyone. I hope my screen is visible.
Yes, so
Okay. So last time we were at Monte Carlo simulations, and today we will go through how it looks on Excel and how can it be implemented. So if you remember, we were looking at the fact that there could be two sources of returns for any asset evolution. One is the long-term mean, which is defined by a deterministic growth rate, and the other one will be the deviation away from that mean, which will be defined by sigma, and the number of standard deviation movement away from the mean. Larger the sigma, greater the deviation, larger the number of standard deviation movement, more will also be the deviation away from the mean. And this can be written as ds, which means change in the stock price or asset price is equal to mu s. Mu is in percentage annualized terms into s will give you the change over a year into dt. So typically in simulation, we take the entire time period and divide the time period into small buckets, each of length dt, and we run a simulation in each of the buckets. So this is the first part of the change in stock price or asset price, and this is called as deterministic change. And the other one is the stochastic change. So that is defined by how volatile the asset is, which is in annualized percentage terms multiplied by S. So that is going to fetch you the deviation, one deviation in absolute terms into root dt will fetch you in a small time period dt. What is the deviation? So we are scaling sigma by root dt and then eventually multiply it by z, and z is the number of standard deviation movement. This term is called as the stochastic term of evolution, and root dt into z is, by the way, called as dw. In stochastic calculus, this is called as Brownian motion, which draws from a distribution which has mean 0 and variance is equal to dt. Why did I write this? Because I'm multiplying z with root dt, and z is n01. So when I take root dt inside, the variance becomes dt, mean still remains 0. So this is the fundamental unit of randomness or stochasticity, which is very popularly used in stochastic calculus, which involves derivatives pricing. So this is called as Brownian motion, this z into root dt. Okay. I can also rewrite this as ds upon s, which can I say is the return in a small time period dt. So ds upon s will be equal to mu dt plus sigma root dt into z. So this is your deterministic source and this is your stochastic source. So more often than not, we use this equation for simulation, and today that's what we're going to do. So let's write a few things here. So we would need certain assumptions. Okay. So let's work with, say, Nifty 50 data. For that, what I would require, see, before we run any simulation, we require mean and standard deviation. Okay. So first we need to either assume certain mean or standard deviation or maybe derive it from historical price action. So what we'll do is we'll derive it from historical price action. So I take Nifty 50 we're going to convert this into stock data. So as soon as I do that, this Nifty 50 gets converted into a financial symbol. And now I write a simple function called as stock history, which you need to feed in certain arguments. The first argument is the stock ticker. The second is the start date, right? Third is end date. Then comes interval, which means do you want daily, weekly, monthly, and some headers. Do you want headers or not? And properties like do you require date, closing price, high, low, etc., etc. So clearly, start date and end date also are required. So the first thing required is symbol. Then we will write start date and then end date. So say start date is 1st Jan 2020 and end date is today. Okay, so let's try to populate the data, historical data, stock history, stock ticker, start date, end date, interval is daily, comma, headers, we would like to see header. So one. Next is properties one. Usually the first column should be the column of dates. So I put a 0. And the next one is I would like to find the closing prices. So 1. So once again, symbol, then start date, then end date, then 0 for interval, daily. 1 is for headers, show headers. 0 is property number 1, which is show date column. 1 is property number 2, which is closing price. Press enter and we find the historical prices for Nifty 50. Yeah, so this is what we have. The next thing is we would like to find the returns. Okay, this mu and sigma are in percentage terms. So returns are needed. This is ascending order of data. So returns will be current divided by previous minus 1. These are arithmetic returns. We can also take log returns if needed, ln of. So in daily time interval, there's not much of difference between ln and arithmetic returns. You can take either or. You can also convert this into percentage terms and increase the decimal. At any point, if you don't understand anything, please, you can stop me. So this is the formula which we've used for return, simple formula. So once we have written, we can find the average, which is mean, and we can find the standard deviation. Average is simple average of all these values. Similarly, standard deviation for all these values. Yeah, let's convert into percentage to decimals. Please note these are daily because we are dealing with daily price series and returns. Obviously, the stats which we get are daily in nature. If you want to analyze, annualized average and standard deviation, we need to just multiply the average by 252, which are the number of trading days. And standard deviation will be taking the daily standard deviation and multiplying by square root of time. Which is 252 trading days we assume in a year. So we get 14 and 18% roughly as the average return and standard deviation. This is over a large sample, which is 5 years. So it's good enough for us to assume this into our simulation. Yeah, so average and standard deviation is what we can assume. And now we are ready to run our simulations. So in the simulations, as we were, saying is We have the entire, suppose we are trying to find the stock price after, say, 22 days. Okay. Which means that I will try to simulate the stock price. So, first of all, I will divide the time period into a day each, maybe. And then I do this over 22 days so that we do it for a calendar month or 22 trading days. And suppose the stock price evolves like this. Then we say, okay, this is path one. Maybe path two, where the stock starts from here, could evolve in this fashion. And we keep on doing this. We keep on running and generating lots of paths. And depending on what we have towards the end, this can be used for two purposes. One is for stock forecasting, and the other one is for derivatives pricing. Because derivatives pricing, we have something called as a payoff function. For instance, for a plain vanilla call option, long call, the payoff function looks like max st minus k comma 0. So this is the st which we are talking about, the stock price. Yeah. So this is how it looks. So we can do it across the entire path. Okay. So let's try to attempt this simulation. I'm going to take these important assumptions here. Start generating some paths. So the first column is say path number. So here clearly we have to generate this. So one way is just write 1, 2 and then drag, but this will take time to drag if there are hundreds of values. So best way is to write a small formula called a sequence. Yeah. Which tells you how many rows you want to populate. Suppose I want 1,000 paths. So this will fetch you the number directly 1 to 1,000. So this is the path number. Yeah. If you want more paths, say I do 10,000, I can do that. It will generate 10,000 values. So that's the path number. The next thing to do is find the deterministic change. Okay, deterministic change, can I say is simple. It's mu s dt. Okay, so now let's do one more thing. Let's get hold of this formula. Let's write it here. So ds is equal to mu s dt plus sigma s root dt into z. Okay, so we're going to use this evolution. So this needs to be assumed. So here we are assuming that the asset price is following a Brownian motion in the stochastic part, where dw is root dt into z. And that follows a normal distribution, mean zero, variance dt. So deterministic part is nothing but mu s dt. Can I say we also need s? So what is the stock price for the simulation? So stock price, can I say, is the last value? Because this is ascending order of data. So this is the last value of index today. So 25,694, we are going to take that as our base stock price or index value. And we can find the deterministic value. Can I say deterministic value is what? Mu s dt into sigma s, mu s dt, right? So what is mu? Mu is this, which is the average. You can also give names to these. Yeah, I can give names to these. I can just write this as index mean and index standard deviation to give some. So how to give names to a variety of assumptions? So select on the left, you should write the name. On the right, you should have the value. Select the names and the values. and you can go to formulas, create from selection, and then check on left column. So essentially on your left are the names, on the right are the values. Press OK. And if I click on this, it is given a name called as index mean. So if I want to reference the annualized mean, I can type index mean. So it acts like a name pointer. So index mean, that is mu, into S. Can I say S is this stock? I can also give a name to this. By the way, you can also select the cell if it's an individual name. Go to the name box and just write stock initial and press enter. So it gives a name to this cell AA1, which is stock initial. So deterministic is index mean into stock initial, which is mu into S into dt. So what is dt for us? 1 day, right? So I can do 1 by 252 because there are 252 trading days. So dt is 1 day. So this is your deterministic part. Okay. What is your stochastic part? So one part done. Stochastic part is mu s root dt. Okay. So, sorry, sigma s. Sigma is what? Index standard deviation into S, initial stock price, into what? Root dt. What is root dt? SQRT of 1 by 252. Okay. Into what? Finally, Z value. Now, what is this Z value? Okay. So before I complete this, let's understand what is this Z value. Z value, as I was saying, was the number of standard deviation movement. So when we have a standard normal distribution, the Z value is plotted on the x-axis. That tells us the number of standard deviation movement. Now the question is, how do we simulate this in Excel? For that, we would need to plot a CDF. So you'll plot a CDF in which y-axis is probability, cumulative probability, ranges from 0 to 1, and x-axis is the Z value corresponding to it. So this is how the curve looks like, the CDF curve. Obviously, it plateaus at 1, starts at 0 probability in the extreme left tail. So what we can do is we can generate a random value using rand function that will generate any value between 0 and 1. And then we invert that to find the Z value. And that needs to be inverted depending on the distribution. Our distribution assumption is standard normal distribution. So we'll use norms inverse to invert it. So first we generate rand, then we invert it using norms inverse. Okay. So how will it look like? So I multiply this. Okay. So first of all, rand and then norms. So I'm just going to show you how to do it first. So rand is just using the rand function. It generates a value between 0 and 1. And then norms inverse is going to invert it and give us what is the Z value. So if only 0.17 probability is the cumulative probability, the Z value is minus 0.95 or close to 1 negative standard deviation movement. Yeah. So how to combine all of this together? Now, the stochastic part we can multiply by. So I can write rand and norms inverse both together. So can I say rand is an input or 0 to 1 is an input to norms inverse? So what I'll do is I'll first write norms inverse, and to that I will input a random number between 0 and 1 and then invert it and find the Z value. So this is your stochastic part. Any questions?
Yes, sir.
Okay. So now, so for explanation, I have, kind of taken both the parts, but now what I'll do is let's do it for day one. And we keep doing for how many days? 22 days, right? For a month. Okay. Now, how do we start? We will start with this. So I'll just copy this. Deterministic part remains the same, right? Every day. So I'll start with this and I will add the stochastic part to it, which is this. Okay. And in one shot, we will get the change in stock price on day one. On day two, so can I say this is the change in stock price, right? But this has to be added to the initial stock price so that we fetch the actual stock price at the end of day one. So I add the DS. So all this is DS, right? This is deterministic. This is stochastic part. Added to S0, we get S1. So S1 is nothing but S0 plus DS1. Yeah, so this is the stock price or the index price at the end of day one. And for day two, just one change we need to do because on day two, your reference cannot be stock initial. Your reference will be the price on day one. So I'm copying the formula, but instead of stock initial, I'll take this as a reference point, the day one's price. Similarly, instead of stock initial, I'll take day one's price as the reference point. So we are now changing the reference to the previous day because simulation is based on the stock value on the previous period. And then I can now drag this formula towards the right. And on this path, the ending value of the index is 25216. It started with 25694. So there's a bit of drawdown in path one. Any questions on this? So my reference is always changing with respect to the previous day. So that's important in a simulation. And once I'm through with this, what I can do is I can now generate all the paths. So I'll just sorry, I've clicked the entire sheet. It's going to get stuck here now. Okay. So it has simulated the values. So we need not do it beyond this. So I'm going to delete the extra rows which are not needed. Just saving the file. So since this is an automatic mode, the sheet, it's recalculating all the cells before when it saves. So which is why it's taking time. Let it just save. Otherwise we'll lose the data. Yeah. Done. So selecting what is not needed and deleting it. Okay, we're done. So the last column BC is going to give us the ending index value. Yeah. Now, what do we do with this? So now we can forecast the stock price. So I can say ending stock price after 1 month. I can say will be equal to the average of these values. So 26020 is the ending stock price. Obviously, every run of the simulation is going to give me a different result. Yeah. And more importantly, it will help us price the option. So we can use it for pricing derivatives. So we'll take the simple example of a long call option. So long call option, the payoff function is nothing but max of st minus k comma 0. So we need to assume certain strike price. So assuming strike price is at the money. So our initial stock price is 25, close to 700. So that's what we'll assume as the strike price. And what we'll do is let's just put a new column here and let's call it payoff. So payoff for say long call option will be equal to max of ending stock price, which is day 22 stock price minus strike price. Assume it is 25 700 comma 0. So these are the payoffs, right? And what do we do with the payoffs? So always when we simulate, okay, so we have simulated from this initial stock price several paths. Towards the end, we get the ending stock price. From that, we can find the payoff. So that will be a column. From the payoffs, we can find the average payoff. This average payoff is at time t. So if you want to find the present value, you will have to multiply by the present value factor. Okay. So call option price will be equal to average of the payoffs, which is this, and you need to multiply by the present value factor. So you can write exponential minus 10% into time, which is 1 by 12. So 10% is R and 1 by 12 is time period because we want to value monthly option. So this is how the pricing looks like. This price assumes sigma of 18%. Please note that was our assumption. Index mean of 18%. Yeah. So once again, this price, how did we get this present value? Or the price of the option today is nothing but e to the power minus RT. So this is basically present value into your average payoff. Now you should see whether this matches with your actual data, right? So we can look at actual data, NSE option chain, and look at monthly. The issue here will be that the number of days left to the month are not going to be 22, right? Because 27 Jan is close by. So we can probably select something which is closer to 1 month from here, 17th Feb. And look at 25,700. Can I say the price is around 265 odd? but we calculated our price as what? 700. And that's because our assumption of sigma, which we have taken, is 18%. But if you look at IV, which is implied volatility, it's at 12% right now. India VIX currently is between 11 and 12. And the IV is for this strike around 12%. This is for the put. I need to look at call. Call is even lower. It's 10.8%. This column is the column of uh, call IV. So 10.87% is the IV for at the money, which means if I make this as say 10 odd percent, it will fetch me a lower value of the option. The option price has reduced. Yeah. We have also assumed index mean as 14%. If the index mean is lower, then that is going to also change my output, the pricing. So it really depends on the quality of my estimates. Okay, what is index mean standard deviation? Hence, it's very important to be in sync with what the market is. So although historical wall or standard deviation was around 18 odd percent, right? But if we go to see right now, the market is pricing the options at 10.8% as the wall. It's pretty low value according to historical standards or precedents. So hence we need to be careful with our estimates. Okay. So this is how simulation happens and an application of the simulation to price an option. Any questions on this?
No, no, sir.
Okay. All right. Let's go to the next reading, which is reading 7. So reading 7 is on sampling. It's a theoretical chapter. I'll any which ways go through the concepts. So there are various ways of sampling, right? So what is the purpose of sampling? Purpose of sampling is to create a subset from a huge population, which is kind of representative to the original population, right? And that's not an easy task. So hence there are several ways of sampling a data set. A classic example would be that you have a Nifty 50 or a BSE 500 index. Yeah. You obviously, suppose you're a retail investor and you have 1 lakh rupees, you obviously can't invest in all 500 stocks, right? So you can't invest in all 500 stocks. So what you do is you take a sample out of it and maybe you invest in 30 stocks. So this is called a sample and your Nifty 500 or NSE 500 is your population. So now the question is, what are the methods of sampling? Yeah. So something which is the most simplest is simple random sampling. So you have a population here and you randomly sample points. For instance, in this, you randomly sample the companies, 530 companies out of 500 companies. Yeah, randomly. So that is called a simple random sampling. So can I say that it's an unbiased method? It has no bias with regards to, or any rule with regards to the selection of the sample. So it's unbiased, which is the implication for using this method. But it doesn't guarantee that all subgroups are covered. For instance, your sample selected could maybe have more of IT stocks or more of banking stocks, but less of auto, maybe less of FMCG. And hence, the fear is that the sample might not be representative. This is the biggest drawback of simple random sampling. Might not be representative. It might not have all the subgroups or might not have enough representation of respective subgroups. For instance, in our index, suppose this is IT and say this is banking, okay? Both are having good amount of weightage on the Nifty 5, Nifty 50, for instance. And say we are selecting, say 10 stocks out of Nifty 50. And if there is hardly any IT or banking stock, can I say those 10 stocks which I'm selecting out of Nifty 50 is not representing the index properly. So subgroups might not be representative. For instance, there is no red dot if this is the subgroup. Similarly, if this is another subgroup, there is no red dot here. So it's possible that in random sampling, some of the subgroups are not given any representation. So that will result in a significant source of error. Okay, so that's the drawback of simple random sampling. So how do you ensure representation? So one of the uh, classical unbiased ways are using stratified random sampling, which is divide your entire population into subgroups or strata. Hence the name stratified sampling. Now these strata have similar characteristics, each strata. For instance, this could be the banking cohort or strata. This could be, say, FMCG. This could be manufacturing and so on and so forth. Yeah. Now what you do is now you sample a few points from banking, few points from FMCG, few from here and keep doing it across every sector. The resulting sample which you have will be representative at least of all sectors. So at least that bias will go out of the picture. Yeah. So risk of sampling error reduces as compared to simple random sampling. Yeah, so it is very useful if you have heterogeneous subgroups which need to be appropriately represented. So your stratified random sampling is a great technique which ensures that. The only uh, supposition here is that, or the criteria here, or the constant is that you should be able to divide or categorize your population into different subgroups, or you should be able to segment your population into several subgroups. If you can't do that, then stratified random sampling won't work, right? So this is stratified random sampling, where we take uh, a portion of the sample from every strata or subgroup which we have created. An example here is, suppose you have 1,000 bonds. Another example, 1,000 bonds in a bond index. Yeah. So first we stratify. To stratify, we need to first uh, divide into various groups the bonds. So here we create two axes. For instance, one is the coupon based on coupon rate and the other based on maturity. So for instance, the first cohort here is having a coupon less than 3% and maturity less than 5 years. So short-term bonds having lower coupon rates is this. Yeah. So now based on these strata, we will sample proportionately. What is sample proportionately? It means that suppose this group's representation in the bond index is only 10 bonds. I will accordingly only sample proportionately from this group. And if this group has say 50, then there will be, suppose this has 10 points, this has 50 points. So can I say in my sample, I will have say 5 of these, but maybe only one of this when I sample, as an example, right? So the number of samples which I select from every strata is based on the representation of the strata in the population. Right, so I need to select proportionately. It's not equi-weighted everywhere. It depends on which strata has the most weightage. So I will select more sample points from those groups. Yeah, so that is what it means. And then I can, once I sample proportionately, I can combine and create a final portfolio, say of 100 bonds. So can I say I'm reducing my the universe by 10%, by 90%? to only 10% of the original number of bonds. So suppose this is 50, so I'm only selecting 5. So I'm reducing my 90% and only selecting 10%. Hence I said if 10 was the representation here of this strata to the overall index, then I only select 10% of 10, which is one bond. So only one bond from the first strata will go into my eventual 100 bond portfolio. Now, the key takeaway here is that although stratified sampling on the surface of it looks great, but it might not ensure portfolio risk characteristics which we want to mirror in the index. For instance, if this index has a certain duration, and if this index has a certain coupon rate, average coupon rate, and if we are trying to mimic that here, it's possible that we might not be able to do that through stratified sampling. Yeah. So might not be able to match the characteristics of the original index. Okay. So there's no guarantee that we do it. But as far as possible, stratified sampling is going to give us values which are close to the original duration and coupon, but still might not be exactly the same. And you can never match it, right? Because you're creating a sample out of the overall population. But any which way, stratified sampling is still better than simple random sampling when it comes to matching these characteristics. So that is what this slide is talking about. Okay. Another method of sampling, the third method is cluster sampling. What is cluster sampling? So here what we do is the population is divided into several subgroups based on the representation of the overall population. And then the analyst will randomly select a number of entire clusters to form the sample. Yeah. For instance, these are the clusters which which will say represent the entire population. So now I can randomly select one of these. So I can either select this, or I can select this, or I can select this. Okay. So that's called as cluster sampling. Now, how does it differentiate from stratified sampling? Please note in stratified sampling, you are dividing the entire population into strata. And then from each strata, you want representation. So that is stratified sampling. In the case of cluster sampling, suppose you have divided the population into clusters, we are only selecting some of the subgroups. Maybe I only select these three and call it as a sample. In stratified sampling, I will have representation from every subgroup. So every subgroup figures in my eventual sample, but in cluster sampling, that's not true. So that's the key difference between stratified sampling and cluster sampling. Any questions? All okay?
Yes,
Yes,
sir.
sir.
So which is more costlier, stratified or cluster?
I think so. Stratified will be cost.
Yeah, because every group needs to have a representation. So you would first need to divide the entire population into subgroups and then select everything. Have a representation of every subgroup. Yeah. So so it is more cost effective, the cluster sampling, but can I say it could have higher risk of sampling error? If the chosen clusters, so these are clusters, if the chosen clusters do not have the perfect representation of the original population, then we have a problem. Then the sampling error will increase. So the risk of sampling error is higher in cluster sampling. So sampling error could be on the higher side, and that happens more if the cluster is not representative of the population. Okay, so this is cluster sampling. What else do we have? We have two other methods. One is convenience sampling. So we are selecting data based on the ease of availability and accessibility of the data. So for instance, an example of that is suppose you're doing a database search. So the first 50 companies that you get, you take the reports and data of those companies. And since those are the most easily accessible, you are doing that and creating a sample out of it. So that's convenience sampling. So typically, since they are not random, it could lead to greater sampling error. It's best for creating some initial exploratory data analysis or checking, but not good for doing any hypothesis testing or if you want to have proper representation of the population. It's not useful there. The other method is judgmental sampling, in which the researcher is going to use his or her experience and judgment to select data in the population, right? For instance, an example could be an accounting analyst is only focusing on specific financial ratios known to be indicators of non-compliance. What is the implication? Implication of sample for a sampling error is it could be high if there's researcher bias. Suppose if I'm, as a researcher, I'm more biased on selecting stocks with low P ratio. So that's my bias as an analyst or as a researcher, and that bias could mean that my sampling error could be high. On the other hand, if my bias is low, then it could lead to a better quality sample, yeah, or more efficiency in my sampling. So that's judgmental sampling. Yeah, and this table gives a quick overview of each of these and compares them. You all can go through it later. I've covered most of it. Uh, there is something called a central limit theorem, which I have covered in the previous session. So here we are going to talk about how sample averages behave predictably, right? Uh, so here the theorem states that you take any population distribution, so you take any empirical distribution, you typically create samples of more than 30 sample size, and you keep repeating this sampling process. And you create a sampling distribution of the mean. So you create the sample and record the sample mean for each. So record the sample mean of each S1, S2, S3 for each of the samples which are selected, and then you plot all these samples, create a PDF out of that. So if your number of samples are close towards infinity, then this distribution will definitely go to a normal distribution in the limit. So the mean of a sampling distribution then will be equal to the true population mean. So whatever is your population distribution, ultimately you end up getting a normal distribution out of that. And this is the basis for selecting normal distribution for many Monte Carlo simulations. Because if you're running millions of simulations, even if the original population density is not normal, you end up getting normal distribution. So that's the power of central limit theorem. There's a very important term called a standard error. What is standard error? Standard error is nothing but the standard deviation of the sampling distribution. Now, this distribution which we got of the sample means. So can I say this is the sampling distribution and this is the distribution of sample means, which are now plotted on the x-axis. So the standard deviation of this sampling distribution is called as sampling error or standard error. Yeah, so that's the definition of standard error. And it is given by this expression. So that's the unknown population standard deviation. Standard error of that is the sampling standard deviation divided by root of n. N is the sample size. So is it a size of 30 or 50 or 100? So the sample size figures in the denominator And hence, can I say my standard error is inversely proportional to the sampling size? So greater the sampling size, can I say lower is my SX or standard error? So higher the number of points in the sample or the sample size, the implication is lower is the standard error. So which is why it makes sense to have a larger sample size. So it's sampling standard error will be lower as compared to see a sample with only 30 points. The standard deviation is higher there. The distribution width increases. Yeah, so that's the significance of the standard error. So our estimate of true mean becomes far more precise and our confidence in the result grows as soon as we increase the sample size. So obviously in the limit, sample size could be equal to population. And there can I say it will exactly match the true mean. And we will have 100% confidence on the result. But that's not possible in real world. And hence we have something called as hypothesis testing to test that out. Yeah. Whenever you do sampling, you need to also understand if your data population is stable or not. For instance, an example of pre and post 2008 financial crisis. Pre, the distribution of asset prices were quite wide and it widened the most in 2008. And post that, with a lot of banking regulations and regulatory risk, uh, parameters like or standards like Basel 2.5, Basel 3, 3.5 kicking in, it has resulted in the shrinkage of the data distributions. And these again widened in 2020 because of the market regime change due to COVID. Right. So whenever we are, taking the data populations, we need to be clear in terms of where is the population. So if your population is having a regime shift in between, we need to be cognizant of that. So your population characteristics pre and post the structural shift will be different. And that's something which a researcher should be cognizant of. Yeah. So this is on the data population stability. And that's that. Any questions on today's session on the simulation? Anything?
So,
No, sir.
So can you guys tell me how will you price an Asian option from this? Suppose I tell you price a long Asian option, call option. How will I price that? If you remember the last time we were doing the payoff, right? Of a long Asian call option. What is the payoff looking like? Max of average of ST, right? Average of the stock prices on all the days minus K comma 0. So I can, goodness. So what I'll do is I'll have another column here in which we will calculate the payoff as max of average of ST. Now average of ST that you take, so let's write it, payoff long Asian call. Yeah. So that will be nothing but max of average of all the STs. What are all the STs? All the stock prices, right? From day 1 to 22. So take the average of that minus the strike price, which is 25,700 in our case, comma 0. So that's your payoff. So it's a path dependent option because the value of the option is clearly dependent on the path which is taken. So, and not the ending price of the stock or the index. And now to find the Asian call option price. We have to just take the average of these values and take the present value of this. Done. Into present value of this, which is exponential of minus RT, which is R is 10% into T, which in our case is 1 by 12. So Asian call option price, as you can see, falls generally below because it is based on the average prices. So it's very much possible that the Asian call option price is cheaper. Similarly, if I take another one, which is look back call option, and I say that takes the maximum value. If you were to compare prices of look back of plain vanilla call and Asian call option, look back call option will have the highest price because that's based on the highest stock price on the entire path. So obviously that price will be the highest. So any exotic option where the payoff has less restrictions, that is more expensive option. Any structured product which has less restrictions, less constraints will have higher price. Any structured product which has or derivative product which has more restrictions on the payoff will generally have lesser price. Those are the ground rules of structuring and pricing. Yeah. So with that, we will end today's session. Any questions you all have on this?
No, sir.
Okay, sir.
All right. See you guys soon then. Yeah. Thank you.
Thank you.
Thank you, sir.